having the honor of having Maik with us. Maik Schenke, I hope I didn't butcher your last name. Sorry for this. From Ansys, who will showcase a few of the most important applications of LS-DYNA in the defense industry. As always, this meeting will be recorded, and you can later access it through our resource hub in our website or our YouTube channel. So thank you, Maik, for joining us.
Okay, yeah. Thanks, Evangelia. So I think I take over, right? So you can see my screen, right? Let me just start the presentation.
Yes, we can.
Yeah. Okay. Perfect. Yeah. So my name is Maik Schenke. I'm working for Ansys now, but actually I started to work for Dynamo like 2017, and then there was the acquisition of Dynamo by Ansys, and now obviously I'm part of Ansys. And I was starting as an engineer, mainly focusing on multiphysics, so everything which is not crash related. So like, I don't know, fluid structure interaction, electromagnetics, and these kind of things. But since last year, I'm part of what Ansys calls it a business development. So basically, the way I understand it is basically meaning that I'm trying to connect sales with the technical parts. So basically, I'm the one who, if you have some idea of what you want to simulate, then I'm the one who's trying to figure out, is doable, is there something missing, what can be done, and then connecting you with the right people. So basically working as some kind of information distributor in between sales and the application engineer. Yeah, I want to show you today a couple of application examples related to defense with LS-DYNA. This is the overview. So first a little bit of overview of LS-DYNA. I'll show you a couple of application scenarios. Basically, I'm currently in this talk, I'm talking about military vehicle design and also weapons design. And of course, at the end, there's a quick summary. So let's talk about LS-DYNA. I mean, when I started with LS-DYNA at the very beginning, I thought LS-DYNA is always about crash and impacts, but this is not the case. So over the years or decades, actually, LS-DYNA grew from this purely structural code, which is the part here in the middle, into what we now called LS-DYNA multiphysics. So we have an electromagnetic tool, we have particles interacting with structures, we have fluids, we have thermal, and everything you can think of these modules as some kind of add-on to the structural solver. So at its core, it's still a structural solver, but supplemented by additional modules. The good thing for you is you don't need an extra license for these modules. So if you get an LS-DYNA license, you can use anything right from the get-go. So there's nothing special you need to know. Yeah, of course, you need to know how to activate it, but from a licensing or from sales point of view, there's nothing to do from your end. Yeah, and when you talk about LS-DYNA multiphysics, you also come across a couple of other terms. So something like one code for all, one model for all in one license, and so on and so on. And let me explain this one model for all a little bit. So what's the basic idea here? Usually when you develop a new product, you have to consider a couple of load cases. For instance, if you take this ball pen here as an idea, you have to think about what are the operating conditions. Yeah, so basically, in this case, you have the pen, you have this activating, you activate the pen, deactivate the pen, and then you have this to do it 1,000 times, and then you simulate this one to get an idea if your design actually works and how good is the reliability. But apart from these operating conditions, you also do have different load cases. Usually they are called then misuse load cases. Yeah. For instance, if you think about a pen, some people get angry and then they try to release the pressure on the pen. So they're starting to bend it. It's a misuse load case. Yeah. Or another one, people get also angry, but in a different way. And then they just throw the pen somewhere against the wall. Yeah, this is the second load case. Yeah, and what you need to do when you design an object, you have to consider all these different loading conditions. The problem is, depending on the scenario you want to simulate, you have to rely on different methods. Yeah, for instance, this one here could be an implicit load case, so it's something slow and static. Yeah, the same here, but this one here, the drop test, is something more fast, quick, and impact like loading scenario. Yeah, but you have to bring it all together. Yeah, and what people usually do is you have your geometry. Yeah, you create a simulation model out of this one. You do your operation loading condition. Yeah, then you take the CAD geometry. Maybe you can reuse some of the meshes, but most of the time you have to convert it again to a to a model which matches your software, and then run this with a different software, and so on and so on. Yeah. So for each load case, you often have, or for one product, you have to incorporate different software tools to be able to simulate different loading scenarios. Yeah. So what is the model strategy is? Basically, you do everything, in this case, with LS-DYNA. Yeah. So for instance, there is what you can do in LS-DYNA, for instance, you can run explicit, implicit models in the same solver. So there's nothing you need to switch. There's a switch in LS-DYNA which you have to activate, and then you can run an implicit simulation with a model which originally comes from an explicit design, or vice versa. I want to be honest here. I mean, some of the features has to be remodeled, but basically you're saving a lot of time because you do not start from scratch all the time. Yeah, you can save a lot of time because the element types are reused, loading conditions, everything is the same, and you're saving a lot of time by doing this one. And then, of course, you can also think about this, putting this into a multiphysics simulation. Again, you're staying inside of the same code, which actually helps you to save a lot of time. Yeah, so this is one of this idea, because I want to get this straight, because a lot of people didn't know what you meant by this one model approach. But now when you come across this term, one model approach is the idea, just do everything in LS-DYNA. Yeah, if possible, if you have crash scenarios, then most people do their crash modeling, and then also to investigate, can we do implicit or quasi-static load cases as well? Yeah, and by this, if this is possible, they're saving a lot of time. Okay. Let's jump into the first section, which is the vehicle design. So here I'm going to focus on land combat vehicles. So when you think about these vehicles, yeah, so this is just a generic military design. You have also, again, different loading scenarios to consider. Yeah, for instance, there's this mine blast. You have to think about, yeah, so what happens to your structure if you expose it to, I don't know, a shock wave or a particle blast? Then, of course, you need to think about NVH, about rough driving. Then you have, of course, the impact onto the structure in terms of how does the impact onto the structure affect your passengers inside. Yeah, this is also something. And then, of course, you have to consider all this kind of NATO protocols for safety standards and so on and so on. So what I want to say is, like, there are so many different type of loading conditions, loading scenarios. You have to consider and bring it all together into one into one product, and in the best case you can do this in one software, which saves you a lot of time. Yeah, but this is the best case scenarios, and of course there's still some mything, and you cannot do anything with LS-DYNA, but just think about, before you switch to a different code, can this be done in LS-DYNA as well? So let's talk about the blast modeling. So this is one of the load cases when you think about vehicles. There are several methods available. You can use ALE, you can use CPM, you can also use the dual CSA method if you want. And the idea in any case is you having a source of a pressure wave, and then it's kind of affecting the structure. I mean, if the pressure wave is strong enough, and of course you can even lift heavily armored military vehicles. And there are different ways of doing this. So for instance, here, this is just the ALE method. This is one way of doing it. You can also use the CPM method together with particle methods. Yeah, so in order to enhance the blast acting onto the structure, there's one way of doing this one. And then the next step is next we going to look inside of the model. So what is actually blast doing on this car? Yeah, so then you can also check for penetration. Yeah, so for instance, here, this is a bullet or a projectile hitting a more brittle fracture. So this could be like a concrete protection or whatever. And then you want to know, okay, what's happening here? So what we're using in this case here is basically a finite element method combined with SPH method. So basically what LS-DYNA can do is, like, if the finite elements reaching a certain failure criteria, they're going to be converted into SPH elements, and then you allow for this defragmentation and also these particles floating around. Yeah, so this is a brittle impact scenario, for instance, with concrete. Another one would be the ductile impact. So this is also the classic one, where you have high velocities, and even though it does look like liquids, I mean, these are, like, of course, not liquids. These are solid materials, but just because of the high impact scenarios, you have these large deformations and making it look like more like solids, liquid-like materials. For instance, here, this is done with the ALE method. Then we also have something which we call the CSA method, which is actually flow mechanics for high velocity flows. So for instance, about when it comes to pressure waves, hypervelocity impacts, hypervelocity flow, so like in engines, rockets, and these kind of things. We even have this reactive flow. Yeah, so this is a simulation my colleagues did a while ago. So this is actually the burning process of inside of a tank. Yeah, they wanted to understand, okay, what's the pressure distribution, what's the propagation, and then also wave reflections of this one. Yeah. So basically, to sum this up, so here we have our design, we have brittle fracture, which you can use with FEA and SPH. You can do ductile impacts, which I think the SALE method is the way to go, or if you have hypervelocity fluid flow, yeah, and also of course this can interact with a structure. Yeah, you can also place a tank in this one or some flexible structure, and it's also always interacting with the fluid flow, of course. The next up, we go into the vehicle, which is then occupant safety. And I'm not sure if you heard it before, but I think like a year ago or maybe 2 years ago, we released this new high fidelity human body model, which was developed from Dynamo, and now obviously part of Ansys. And the idea was to go all in with the details when it comes to human anatomy. Yeah. So the idea was, don't make any compromises already. So just go in, try to have as much detail as possible. So for instance, we took all the muscles and we did not simplify it in some way. Yeah, so you don't find any line elements representing some muscles or ligaments or tendons. It's all modeled as solid elements or as shell elements at least. Yeah, to have the most high fidelity human body model and to keep it as general as possible so that we do not restrict our further application in some way by already having simplifications at the beginning, but try to be as general as possible. And this is the outcome of the Hans. Currently, it's heavily focused on automotive industry, but we're already investigating an application when it comes to military applications. For instance, so you can see here, these are the first tests with a blunt impact. Yeah, this was 35 kilometers per hour. This is the typical scenario when it comes to automotive. Also this one here, a belt tension. But you can also think about this one. This could be also military applications. For instance, if you have a protective vest, a bulletproof vest, for instance, then the vest is distributing the impact load of the small projectile onto a bigger surface. And at the end, what the body is expecting or what the body is seeing is some kind of more blunt impact. Yeah, so this is what we're going. Another one here. This is this one here. Then this classic automotive impact with a head impact. Yeah, so then we want to know what is the chances of a concussion if we have a head impact, and then how I don't know how to call this, the brain fluid is distributing the load onto the brain, and it's that chance of concussion. Also here, this is an impact. This is a scenario which is more going to the military applications. Yeah, so this is like a helmet onto a pilot during the emergency ejection, and how this is affecting the spine and the muscles, and is there a chance of can we redesign the seat a little bit to keep the people as upright as possible to avoid this kind of whiplash behavior here in the neck area. So these are questions we want to answer. Yeah, but this is like automotive is the more established part, but now we're roaming also into new application scenarios, and in this case we're also looking into military applications. Okay, next up is weapon design. So here also you have to think about, you have to kind of deal with different kind of phenomena. Yeah. So if you do, for instance, depending what you do, is if you do like non-linear structure analysis, so you just focus on the structure with the impact, then probably LS-DYNA is the way to go. If you have something which is more like fluid dominated, then probably Ansys Fluent is the more powerful fluid solver. However, when you come to component level dynamics, yeah, so have rigid body motions and something, then Ansys motion is the way to go. And the last case is when you want to combine it, yeah, then you can think about LS-DYNA as either you do it in code with LS-DYNA, yeah, because you have this coupled fluid structure interaction already built into LS-DYNA, or you think about, well, I just have a weak coupling and I need a more powerful fluid solver, then you go with Ansys Fluent and use the intrinsic coupling possibilities to go. So it highly depends on what you want to do, but there's no general recommendation we can give here. It just depends on the very particular case. And if you have questions, feel free to reach out to Simtech, or they reach out to us, or we reach out to us directly or something like this. It's up to you, and then we always find a solution. Okay, so one example is the in-bore analysis of the bullet inside of the machine gun. So the question we want to answer, first of all, what is the stress exerted onto the whole inner diameter? We want to know what's the idea of the friction. We want to know what's the heat generation. So it means basically addressing the topic, how many bullets can you shoot through this the rifle till it gets too hot or getting too warm. And then it's becoming inaccurate because it's of the heating. You have like a thermal deformation. So that's the idea of this one. And this was done fully in LS-DYNA. So you have the bullet, it's starting to spin. You can see here we have plastic deformations on the bullet, which also affects creating the friction area, and then the friction area creating some generating heat, and then this heating up the rifle, the shaft, in this situation. And this is the answers we want to question. Also here, like I said, this is a fully dynamic coupled thermal analysis. If you wish, you could also add like a fluid flow around this one, or maybe also on the inside to basically accelerating the bullet by some, I don't know, by some explosion, by some reaction, and then having the full model and simulation. Okay, then there's the other one here. Once you have accelerated the bullet, at some point it will leave. It will be released, and then you, of course, you want to know, okay, what are the shock waves propagating, especially if you think about big tanks. As soon as the bullet is leaving it, you also give way for the pressure wave to roam into the free area, and then you want to know how far away have the people stay away from the bullet or from the tank in order to be safe. Otherwise, they get hit by the shock waves. Or you can also investigate how we have to redesign this part of the cannon in order to avoid or disperse these shock waves into the environment, to have less impact. And you can do this with either the SALE method in LS-DYNA, or you can use the CESA method, and to do this fully structured, fully coupled fluid structure interaction simulation, of course, and this is also coupled with thermal effects. Another one is so-called shape charges. So basically what you do, let's just stop this here, is a shape charge is the weapon design, which is starting automatically. So what is generating the projectile by when you fire the weapon. So for instance, this is like an explosive, this is some kind of container, and this is some kind of usually some copper-like material, and you're going to ignite it, and then you want to design your structure to be stiff enough, and also how you want to know how this projectile is shaped, and then of course once the projectile is shaped, you also want to know how does this one impact my actual target, so to say. So you're going all in. You have to be creating the ignition process with the generation of your shape shape charge, the projectile when it's built, it's going to set up, and then when it's hitting your target. This is, by the way, I think this is an ALE method in this case. And last but not least, one of very often questions we get, or the questions you often have, is how robust is my design? That means if I have designed a certain machinery, or maybe, I don't know, a bullet or whatever, and you talk to your supplier for the materials, you want to produce it, and it turns out like, I don't know, the quality of the material you're getting is not perfectly fine, it's not as expected. So you want to know how does this deviations or scattering of material data or material input alter my performance of my product. So for instance, if the sheet metal is not 2 millimeters, but maybe 2.1 millimeters or just 1.9 millimeters, how does it affect the I don't know, the performance of my product? And what you have to do is you do a so-called robustness analysis, or sensitivity analysis. So you kind of take your simulation model, you're going to modify these parameters, and then run a simulation again. And you can think about, depending on the number of variations possible, if you do this all by hand, there's a lot of simulation work to do. So each simulation has to be set up by an engineer, you run it, you have to evaluate the results, and then put it all back together. There are simple ways to do this to automate the simulation workflow for this kind of robustness analysis. You can do this with LS-opt, you can use OptiSlang, or maybe you can also use PyDyna, but I would say this is LS-opt and OptiSlang are the ones designed for. Yeah, so for instance, this is a longitudinal member of a car beam in a crash circuit scenario, where we're going to change and vary the thickness a little bit. And then what LS-DYNA is doing, or LS-opt or OptiSlang is running all the simulation, the variances in the background. And at the end of the simulation, you get this kind of plot where you can see, well, if I change the thickness of my sheet metal, for instance, I do find the highest impact in this area and the lowest impact in this area. So that means, as an engineer, you can tell, well, if my material input is fluctuating in parameters like in, I don't know, material properties or in sheet metal thickness, this area will be affected, and this area will not be affected. That means if this is the important area, you can easily go away with, I don't know, lower quality material, so to say. Yeah, however, this is affecting this area, the biggest effect, and this is the important area for you. Then probably you have to talk to your supplier and see what they can do for you. Yeah, but the idea of this one is do this robust analysis, sensitivity studies in an automated way to save you a lot of time when it comes to this kind of, I don't know, material property scattering simulation. Yeah, and that of course becomes more important when it comes to more complex designs, also shape charges. Yeah, thickness of this container here, how does it affect the result, the formation of your projectile, and so on and so on. Yeah, so this is like making your life a little bit more simple. Okay, this was a quick rush through, and the take-home message is, first of all, LS-DYNA is more than automotive crash nowadays. Yeah, actually, I want you to keep in mind that if you think about LS-DYNA, think about this strongly coupled multi-physics solver. Think about this all-in-one approach. Think about this one model strategy, and think about that. If you have an LS-DYNA license, you just can use all these different kind of additional add-ons, electromagnetics, fluid mechanics, particle mechanics. You can use it all right away, and this is all coupled with structural mechanics. Yeah, and of course, also to make your life easier as an engineer, the integration into all the Ansys products, other Ansys products, becomes more and more. Yeah. So, for instance, there's a heavy development which we see here in this Ansys workbench, or the mechanical integration, to also support LS-DYNA simulations. And every year there's a lot of development going on to support all the methods in LS-DYNA through this mechanical interface. So if you're a mechanical engineer, you can reuse your own knowledge, what you did so far, and you can easily run LS-DYNA simulations. At least the basic one, you will need a little bit more how when it comes to this multi-physics, but you can just reuse your mechanical know-how and start with LS-DYNA as a starting point, and then you can grow from there and become a more holistic, so to say, simulation engineer. Yeah. So basically, this is the take-home message. Yeah. So with that, thanks for your attention.
Thank you, Maik. Thank you so much. So thank you all for joining us at this webinar. As always, you can address any questions that are after our webinar directly to us, and we can also involve Maik if we need to.